So for this video, we're going to take a look at everything we've looked at dealing with triangles for this unit test that's coming up. So first, we talked about the centers of triangles, and we have 4 different centers that we look at, and they're all made by different segments within the triangle. So one of the ones that we looked at is the orthocenter, and the orthocenter is formed by altitudes. And remember, your altitude is like the height, so it has to come from a vertex and drop straight down to form a right angle with the opposite leg, or the opposite base. All right, so if I have 3 altitudes, they are going to intersect at the orthocenter. There's not really much that's special about the orthocenter, other than that it's where the altitudes intersect. Right, our second one, or another one, is the point where, let's get my triangle drawn, the point where our perpendicular bisectors intersect. So remember, a perpendicular it forms a 90-degree angle, and bisectors means it cuts it in half, and it's talking about cutting the segments in half, or each of our sides. So if I go to the midpoint on each of my sides, and then draw a perpendicular bisector. All right, this point where they all intersect is our circumcenter. Right, our circumcenter does have another special property, and it is that, remember, it comes from the sides, so it's going to be equidistant from all of the vertices. So all of those are the same. All right, another one we have is angle bisectors. All right, now instead of bisecting and going through the midpoint of the side, it's going to bisect the angles. Okay, that was not a bisector. Let's try that one again. Better. All right. And where all 3 of the angle bisectors meet is our incenter. And the incenter also has a property like our circumcenter, but remember, the circumcenter comes from the sides, so it's equidistant from the angles, from the vertices. Our angle bisectors come from the angles and the vertices, so they're going to be equidistant from the side. And not just equidistant, but equidistant at a right angle. So everywhere that it meets at a right angle is the same. And our 4th center is our centroid, and that is where the medians intersect. And the medians connect vertex to midpoint of the opposite side. So all of these are going to be the same. And I'm just going to go vertex to midpoint. All right, and that is our centroid. And the centroid actually has 2 pieces of information. One of them is that it's the center of gravity. So you could balance it on the centroid and it would stay flat. And the other one is that it's 2/3 from vertex to midpoint. So that just means that if I consider this whole thing to be 3 parts, so 3x, that means that the long side from the vertex is 2 of the parts, and the short side to the midpoint is 1 of the parts. So we have 1x, 2x, and the whole thing is 3x. So if I'm given the short, I can double it to get the long, triple it to get the whole thing. If I'm given the long, I can divide it by 3 to get the short, and then double that to get the long. If I'm given the whole thing, sorry. And then if I'm given the long, I can cut it in half to get the short, add it together to get the whole thing. So these are the 4 centers of our triangles. Now it's important to not just know what they're called and what they are special properties are, but it's important to know what they do, because sometimes, like if they tell you it's an incenter, you know that the angles are cut in half. So you can use that to help solve for x if they're asking you something about the angles. The rest of our unit was pretty much review. So we have classifying triangles. We have 3 different types based on our sides, and that's scalene, isosceles, and equilateral. And for our angles, we have acute, obtuse, and right. All right, and you have to be able to tell if it is a triangle, and if three sides form a triangle, like 3, 5, and 7, the sum of the smaller two must be bigger than the third side. So in this case, 3 plus 5 is 8. 8 is bigger than 7, so that is a triangle. Okay, and you use that as well to find the range of the third side, because the sum of any two sides must be greater than the third. So you can create your three inequalities, or the shortcut is to add them and subtract them. All right, then we have to also decide if it's acute, obtuse, or right, right? Because you can look at the side lengths to tell if it's scalene, isosceles, or equilateral. We want to know about the angles as well. So one option, look for your Pythagorean triples. Remember, our triples, our common ones, are 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25, or any ratio of these. And there's a bunch, but these are the very common ones. So if you recognize these, you automatically know it's a right triangle. If you don't recognize them, then you can plug them into our Pythagorean inequality theorem, which says that if c squared is equal to a squared plus b squared, it's a right triangle. If c squared is bigger, it's obtuse, and if c squared is smaller, it's acute. All right, so you got to be able to tell and classify what the triangle is based on sides and angles. All right, we also looked at congruent and similar triangles. So congruent postulates, we have side, 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 if all of our sides are the same. If two of the sides and the included angle, which means this is the angle that touches both sides, and then if two of the angles and the included side, and then if two angles and the non-included side are the same, all of these tell us if they are congruent. And there is one time that we are allowed to have two sides and the non-included angle. Obviously, that's going to be our bad word, so we don't use it except for when it's a right triangle, and then we switch it to hypotenuse leg. So if I know the hypotenuse of a right triangle and I know the leg of a right triangle, I automatically know the third side because of the Pythagorean theorem. So the triangles have to be congruent. So if I know that it's a right triangle and hypotenuse and leg, it's got to be congruent. Similar, we have angle, angle, because if I have the congruent angle, it's got to be the same shape, just not necessarily the same size. As well as the three sides, and remember this is proportional, not the congruent. So you write your ratios, and if all the ratios are the same, then the sides are proportional, so then it's similar. As well as side, angle, side. Technically, angle, side, angle, and angle, angle, side work as well, but as long as I have the two angles, then I know it's going to be similar because of angle, angle. So here I have angle, side, angle. Well, as long as I have two angles, I'm set. So technically, all these work for similarity as well, but angle, angle is an easy one to get. All right, geometric mean. Remember, geometric mean is looking for a value such that you have the same value on the bottom of A and on top of B that makes it the same. So our formula for geometric mean is that the geometric mean x equals the square root of A times B. And this is important because if I have a right triangle and I drop an altitude from the right angle, I'm going to get similar triangles. Now, you could use your similar triangle rules to figure this out, but it ends up being the same thing because our similar triangles, the sides are proportional, such that if I call this my height, and I call my two segments on the bottom that the height cuts it into, A and B, the height is going to be the geometric mean of A times B. Likewise, if I call my slanted sides P and Q, and then I call this whole thing C, I know that my new hypotenuse of the left triangle is going to be equal to the geometric mean of that base, A, times the original hypotenuse, C. All right, and Q is going to be the same thing, but with its base, B, times the whole thing, C. And again, this is just because of similar triangles. If you were to think about it, this hypotenuse here has to have a ratio with the original hypotenuse, C. And then my height here, A, has to have a ratio with the original triangle, the P here. Right? So if I were to write all that out, I would end up with a fraction like this, a proportion like this, that would then simplify to the square root of A times C. Alright, so if I wanted to find missing pieces of a right triangle that's cut into two similar right triangles, I can use geometric mean. All right, special right triangles, we have two kinds, 30, 60, 90, 45, 45, 90. Our 45, 45 is also isosceles, and it comes from the square. So that means that both of our legs are the same. Then to go from legs to hypotenuse, we multiply by root 2. 30, 60, 90 comes from an equilateral triangle, and we have two different angles, so we have two different sides. Start with the short side, which is opposite the 30-degree angle, the smaller angle. To go from short to hypotenuse, we double it. Short to long, multiply it by root 3. And then we have right triangle trig, which is what we use SOHCAHTOA for. Alright, so we have sine, cosine, tangent. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And the opposite, adjacent, hypotenuse are just all the sides in relation to the angle that you're working with. So if I have a right triangle and I'm working with this angle theta, opposite's going to be the side it does not touch. Adjacent's the side it touches that's not the hypotenuse, and your hypotenuse is always the side that's across from the right angle. So you use this to look for sides and angles. So if I wanted to find, if I knew that this was 51 degrees, and I'm looking for this side, and I know that my hypotenuse is 14. In relation to my angle 51, x is opposite, 14 is hypotenuse, so that's sine. So I would say sine of my angle 51 equals opposite x over hypotenuse 14, and then multiply both sides by 14. And then I could type this into my calculator. If I was looking for an angle, so let's say I'm looking for that same angle theta, but I know that this side is 7 and this side is 11. Right? Now I'm given adjacent to my angle and hypotenuse, so that's going to be cosine. So we can say cosine of theta equals adjacent 7 over hypotenuse 11. Then to cancel out a cosine, I take the inverse cosine of both sides. So this is going to go away, and then in the calculator, do second cosine to get to your inverse, 7 divided by 11. All right, so that is everything in our triangle unit, from special right triangles and right triangle trig all the way back to the centers of our triangle and classifying different types of triangles.